think we can start. Is that okay?
Yeah, so thank you everybody for joining the session here. We're going to go ahead and get started. We've got Samya and Samya, hopefully I'm saying that right, here. We've got an amazing talk from them and with different experience backgrounds. One of them is a PhD computer science student at the U of M, and another is a software engineer at Microsoft. So it's great to have you two working together on this. And they're going to be talking here about computer vision and using it in rainforests. So that's really awesome. I'll let you guys kick it off.
Thank you. I hope everyone is doing great and having fun today. So every day in our lives, we see the impact of artificial intelligence, whether it is a simple text query on Google or ad recommendation on Facebook and Instagram. The impact of having our computers learn from historical data is pretty evident, especially in the commercial domain, where companies try to analyze our data to help achieve their business goals. But machine learning and AI also presents many opportunities that would, in the long run, contribute to the betterment of the society and contribute towards sustainable development for the society. And in this case, the onus lies on our shoulders to make proper use of these tools that we have at our disposal. So this session will focus on computer vision and its application in geoscience field. Last year, me and my friend Somya were working on a deep learning project that revolved around the usage of deep convolutional neural networks on satellite imagery data. And that's also what we will be talking about today towards the latter half of the presentation. So deforestation in the Amazon rainforest basin is currently a massive threat to the biodiversity and climate. By 2018, it was said that 17% of the rainforest had already been wiped out, and research suggests that anything between 20 to 25% would be the tipping point of no return. So there are several factors that are contributing towards this. Illegal farming, slash and burn methods, crop cultivation that started in the 1960s, and then the oil drilling of fossil fuels reservoirs that started in the 1970s. So there are like a lot of things that contribute towards deforestation and biodiversity loss in the Amazon rainforest. But better data about the location of deforestation and human encroachment on forests can help stakeholders respond more effectively. Remote sensing data has dramatically improved our knowledge of the basin. Lower costs for obtaining satellite-based imagery has led to a larger scale study of Amazon, and perhaps it's the only possible way to study Amazon at a very large scale. With this objective of tracking human footprint in Amazon, we want to understand how habitation and other human land use leads to deforestation. First, we'll be looking at what is computer vision, then its application in geoscience, and then we'll be talking about the project that we undertook last year. So, computer vision is an extremely vital part of artificial intelligence domain, where we focus on building and deploying machine learning tools that help computers learn from visual cues. That is, we use images and videos as input and expect the computer to solve a problem for us. It is also interesting to note that computer vision is a very vast interdisciplinary field that draws from very different fields, that not only relies on machine learning and AI, but also draws from fields like signal processing, digital processing to identify patterns and signals in our images. And it also draws from fields like mathematics and physics that take into account physical laws and physical constraints that govern our real world to make reasonable predictions. If we look around us, we can find a lot of examples of computer vision applications. There are several scenarios that benefit from the autonomy and the objectivity and the scalability of computer vision. There is a lot of novel research going on in healthcare. Our healthcare professionals, like radiologists, are generally burdened with a lot of patients simultaneously. So it is difficult for them to always make the right call objectively. So that's where computer vision comes in to help them with tasks like finding anomalies in medical images so that they can diagnose diseases more effectively. Similarly, the manufacturing industry relies on data analysis tools for quality control. And computer vision can look at incoming pictures or videos of products and processes to ensure that there is nothing wrong with them. Similarly, computer vision can help with facial recognition for security purposes and can also help with scanning surveillance footage and images for law and order officials. Computer vision has become an aid for faster and more objective problem solving. But behind the hood, from an AI perspective, what really is going on is there is a machine learning model at play, which is called neural network. It helps us in analyzing visual information. Usually, we first convert the images or any other visual information that is into numbers or arrays of numbers that convey information like the grayscale value at pixel level or red, green, blue pixel values or additional depth perception information. This numerical information can then be cleaned or changed in a way so that the neural network model can pick up as much signal as possible. Just like any other machine learning model, neural network models try to solve a problem. And that problem solving usually involves understanding how a set of variables called the feature set influences or impacts another variable called the target variable. The neural network sees the feature data and then corresponding target values. For example, the model sees an image of a dog. The features are the pixel values in all of the pixels in that image, and the target is a label telling us whether there is a dog in that image or not. So that the model sees many such images and corresponding image labels and learns how a dog looks in terms of pixels and pixel values. It does that by learning a series of mathematical transformations and feature mapping. So we give the features to the neural network through the first layer, as shown on the right-hand side image. And then the neural network transforms those features in the hidden layers in the middle and learns to produce an output in the form of the target value in the output layer. Each layer consists of several nodes, which can be thought of as features, whether it's the original input feature or a transform feature. And there are usually many hidden layers stacked one after another, and we use a mathematical function called activation function to perform those transformations and learn those transformations in the neural network model. Finally, after the model learns whatever there is to learn in the images, we can give it a new image that it has never seen before, and it will tell us what the value of the target variable should be. So for image data sets, we usually use something called the convolutional neural network, which is a more advanced form of neural network. It not only learns those transformations in the hidden layers, it also learns how to filter or compress that information for more efficient learning. This is because when it comes to images, we not only have to learn many images, we also have to take into account that each image is a dense collection of information. And we have to parse that through our CNN. So the number of parameters that we have to learn through the training process grows very rapidly if we use a neural network instead of a CNN model. And that's why we use a CNN model for images. In the image on the left, we can see instead of a 1D array of input nodes, we have a 2D array of nodes. This is a more intuitive way of laying out the pixel information in an image in a 2D form, like a 2D image. There are several operations or transformations that happen between the two layers in a CNN. The first operation is called convolution. And the primary purpose of convolution in the case of a CNN is to extract features from the input image and preserve the spatial relationship between pixels by learning image features using small squares or smaller subsets of input data one at a time. In the right-hand side GIF, the red and the green box is called filter or feature detector. And the matrix formed by sliding the filter over the image and computing the dot product with the original subsection of pixels is called feature map. Filters act as feature detectors from the original input image. So here we can see in the GIF that there are two different filters and they produce two different feature maps, and the filter hyperparameters can play an important role in that learning process. Due to time constraints, I will not be talking about the details of convolution operation, but if you look it up on the internet, you will see it's a very interesting thing. The second operation that's mentioned in this image is subsampling, or it's also known as spatial pooling. The spatial pooling helps us in reducing the dimensionality of each feature map, but it also retains the most important information. And spatial pooling can be of many forms, but the most important and the most popular one is max pooling, where we define a spatial neighborhood and take the maximum valued element from each of that spatial neighborhood for better representation. We will be discussing the technical details of the architecture of the convolutional neural network that we use in our project in later slides. But right now, we'll be talking about the application of computer vision in geoscience.
Right. Thank you, Somya. So, geoscience, what exactly is geoscience? Geoscience is essentially the study of geophysical problems in nature. So this could be something like predicting impacts of climate change, measuring air pollution, predicting increased risk to infrastructure. This could be because of natural disasters or man-made disasters, modeling future availability and consumption of resources such as water, food, mineral resources, even identifying factors which are responsible for earthquakes, landslides, flood, and volcanic eruptions. So if we basically put it in a single sentence, it would be about understanding the Earth system, the way it functions, and the way the different components interact with one another. Essentially, geoscience data is collected from three broad data sources. One is satellite imagery, that is it is acquired from remote sensors that are present on the satellite, and then we are able to process those images. The second kind of data is in situ. These sensors would be present either in the sea, land, or in the air. And the third kind is simulation data that is generated from physics-based models of the Earth system. If we move on to the next slide, we see that there are a lot of properties that are associated with geoscience data, which serve as both boons and banes when we are working with this kind of data. So I would like to especially mention about these properties that you see on the screen. So there is space and time, which works both as a plus and as a minus. I would say space and time, it's a plus, because when we talk about spatiotemporal features of the data, we essentially mean that it would be in a way that they are correlated, really highly correlated in terms of space and time. That's because if there are two data points which are essentially referring to the same location, it would show similar features in like time stamps which are like right next to each other. So if I'm talking about a particular city, it would have similar features at 6 in the morning and 6:15. So basically, it helps us in analyzing the data points or like filling up for missing data. Similarly, if you're talking in terms of space, we could have, given a particular time of say 6 a.m., cities that are right next to each other would be having like similar geospatial information. So this is a plus because it helps us with the kind of data that we're working with. But again, it can also serve as a negative point because there is also very high variability, or we can call it heterogeneity in space and time, That's because there could be different kinds of vegetation, different rock formations, or climatic conditions, varying geographies, etc., which all are a large number of factors which we don't even yet know all about, which play a very important role in understanding the data that we are working with. So there could be like seasonal changes or like decadal changes, etc. We could have long-term or short-term changes which are actually playing a huge fact, being a huge factor in determining these things. The second thing is high dimensionality. So like I said, each data point would have a lot of factors that are actually contributing. So this is definitely hard to work with. That is because we could have like so many different definitions associated with each object that we are able to perceive, things that we don't know yet. It could be that we are receiving a certain amount of data from the sensors, but we don't know yet what it is. So we don't have the knowledge to label them correctly. We have data coming in from multiple sources, multiple resolutions. So that all plays a part in pre-processing the data before we are able to work with it. And apart from that, there are a lot of rare classes. This is basically attributing to the high dimensionality of the data, that it becomes a little hard to talk about the class imbalance, etc., associated with this data when we are working with it. Apart from that, we have poor data quality. Poor data quality essentially means that there is a lot of data that could be missing, or it could be incorrect. It could be happening because the sensors that are capturing this particular data, they could have stopped functioning for some reason, they could have failed, or they could have interfered with one another, resulting in a loss of the data that we have. And apart from that, there's also the paucity of ground truth, as you can see on the slide. That essentially means that whatever labeling that we have for this particular data is subjective in the sense that it is basically best of many votes that are cast in order to label the data. So there is no real true ground truth that is available for a large amount of data that we deal with. And all of these factors actually play a huge role in being able to model our data to a certain neural network or something, so that it is able to classify and give a good performance. So these are things that basically impact the geoscience data analysis. So if we move on to the next slide. Right. Moving on to the project that we worked with. So this particular data set that we used was by Planet. It was essentially a Kaggle competition that was about the Amazon rainforest. It was essentially to detect deforestation in the Amazon rainforest and the effect or the presence of human activity leading to deforestation. So we had around 40,000 Kaggle chips. As you can see on the screen, a Kaggle chip is about 256 by 256 pixels and a 3.7 meter GSD. And each of these Kaggle chips was basically consisting of both land use labels as well as atmospheric labels. Overall, we had 17 classes or 17 labels. What it means is that we had 4 atmospheric labels, which were basically clear, partly cloudy, cloudy, and hazy. And these 4 labels were mutually exclusive. So we couldn't have two kinds of atmospheric labels associated with a single chip. And we had a lot of land use cover labels, which was basically like we had roads, water, agriculture, even rare labels like cultivation or slash and burn and such. You can have a good look at all of these labels when we move on to the further slides. And apart from that, we used like 2/3 of the 40,000 chips for training, and we used 1/3 for testing. So in this slide, if you see the data set, go on to the next slide. Yeah, in this slide, if you see the data set is consisting of both atmospheric and land use labels, like I said. So there's at most one atmospheric label which got associated with every chip. But here, primary essentially means primary rainforest. So you would see that there are multiple land use labels that are associated with every chip here. So you have haze, which is like the atmospheric label, but we only have that one atmospheric label. And then there's primary associated with it, which is primary rainforest, which is a land use label. So primary has coexisted with like cultivation, like shifting cultivation and such, as you can see. So this is the kind of data set chips that we had. So if we move on to the next slide. This is the class imbalance that I was talking about. Like I said, there are a lot of rare classes that happen, especially when it comes to such kind of data. So you can see that primary rainforest, now we were talking about the Amazon forest. So there is like a large number of chips that got classified with primary rainforest and with clear skies. And apart from that, if you go further down, you will see that slash and burn, conventional mining, and these kind of labels were very rare. So there was this whole class imbalance concept that we had to take care of while we were working with this data set. So I hand it over to Somya now.
Yeah, so apart from the class imbalance that we talked about, another challenge that we face with respect to our data set is that there's a lot of class correlation. For the atmospheric labels, it's simpler because one image cannot have multiple atmospheric labels. So it can either have a clear sky, or it can either have it could either be partly cloudy, or it could be hazy. So for the atmospheric labels, it was simpler, but for other land use labels, there was more class correlation. For example, cultivation and agriculture coexist in the same image chip. Similarly, habitation and agriculture could coexist in one image chip. So, and on the right-hand side, you can see the co-occurrence matrix, which tells us about how frequently did two of the classes coexist in images. So as we can see that there were a lot of images that had primary rainforest cover in it and clear sky. And similarly, we can see, since we had so many primary rainforest cover images, there is a lot of co-occurrence and coexistence with other classes as well with primary rainforest. So it's very important to understand and explore your data set and the data set attributes before you go on to modeling, because those data set characteristics define the nature of your problem and also influence the kind of model that you will be applying. So to summarize our data challenges and attributes, the first one is the classification problem and the kind of classification problem that we had. Not only is this a multi-class problem where each image can have one of the 17 classes as labels, but also that each image can have multiple labels at a time explaining each component of the scene in an image. For example, an image can have both road and water, or there can be other combinations that exist. The second is the class correlation. So there are certain labels that coexist quite frequently, whereas there are others that do not. And the third one is class imbalance. Since there is an extremely high class imbalance, this means that there are more samples for one class than the other class in the data set. And so the machine learning model has a better chance of learning those classes which have more images present in the data set than the ones that are not present. So all these attributes of the data would require the model architecture modifications to incorporate them. So moving on to more technical part of our presentation, the first architecture or the first neural network, the convolutional neural network that we applied is a modification of the Inception model or the GoogleNet model. So Inception is the name of a convolutional neural network architecture that was proposed by Zagheri et al. In 2014. Not only did it use multiple loss functions for training and use ReLU nonlinear activation for the first time as compared to the architectures that existed before 2014, but it was also the first architecture to have parallelly laid out layers, hidden layers. So from a theoretical point of view, the researchers observed that by introducing sparsity, by introducing sparsity in the form of multiple convolutional layers parallelly, really helped with efficient feature representation learning with nearly not as many parameters. And on the left-hand side, what you can see is the inception block containing multiple layers. And on the right-hand side is the whole inception model architecture, where we can see that these blocks are stacked sequentially. And this architecture is very popular since it performs so well. And since 2014, there has been several modifications and improvements that incrementally increase the task performance of image classification. And all that merits its own talk since this model has so many different aspects to it. In our first baseline, instead of taking the whole inception architecture for training, we used only 2 inception blocks stacked sequentially, and that capped our number of layers to 100 instead of the 300 layers that are present in the original inception model. So we used sigmoid output for the land use labels and softmax output for the atmospheric labels. And we used binary cross entropy loss function for training and learning to account for the class imbalance. We used 2/3 of our data for training and 1/3 for testing. And this is the results that we got for our first baseline model. So the average F2 score is 68.15%, and our accuracy is at 92%. The accuracy is high because the model did a good job with the classes with more images, like the primary rainforest cover class and the clear sky class because of the high class imbalance. But in case of high class imbalance, it is prudent to use some other metric like F2 measure or the F1 measure instead of accuracy, because these account for the false positives and false negatives that the accuracy cannot account for. So here we can see that the F2 score is not as high as the accuracy, and we try to improve our F2 score in further models. But before we go on to the next architecture, we can look and visualize the performance in terms of prediction. So here are 4 different images and 4 different predictions for those images. Since we use softmax output function for the atmospheric labels, the model did not predict any 2 atmospheric labels at one time for one picture. Even so, the class imbalance affected the performance a lot despite using cross entropy loss function. We can all see that the images are predicted to have clear sky, whereas they do not. Also, all our predictions have road and agriculture, which are one of the majority classes, but in reality, not all of the pictures have those present in the scene. So next up, we have another CNN architecture model with a better performance than our first baseline.
Right. So the second architecture was like a custom model that we made, a CNN model, which implemented Bayes normalization. As you can see, there is like a basic idea of the model that we used. It had 4 convolution layers, 3 max pool, 2 fully convoluted, and 3 dropout layers. So it basically implemented sigmoid output like Somya talked about, and we used binary cross entropy loss and atom optimization. So dropout is something that's new that you see on the slide. Dropout is essentially a regularization method that approximates the training of a number of neural networks with different architectures. It is essentially used to tackle the problem of overfitting in neural networks. During training, some number of layers layer outputs which are there, they are randomly dropped out or ignored. And what happens is that it has the effect of making the layer look like a layer with a different number of nodes and connectivity as compared to the previous layer. In effect, what happens is that each update to the layer during training would be performed with a different view or a different perspective of the configured layer. Like I said, it's basically a way for us to avoid overfitting when it comes to neural networks. So this was the architecture that we implemented. If we move on to the next slide, the results here, as you can see, the cross entropy loss, the loss was lesser. We have better accuracy and better F2 score as compared to the Inception model. If we move on to the next slide, so these are some of the scene examples that you can see. That is essentially a few of the chips that we worked with. Here you can see that the difference is like earlier, like how it happened with the Inception model. It started predicting. So the difference here you can see is that the atmospheric labels are not exclusive. The reason why this happened was because when we were implementing the custom CNN, we did not include a softmax layer for the atmospheric labels exclusively, which is why we have sigmoid output, which is the reason why you see like multiple atmospheric labels predicted. As we move to the next slide, you would see two other chips of a similar kind. Again, here you can see that agriculture and roads were predicted. Water was one of the labels which had like a good number of samples. So that is something that got predicted. One interesting thing that we noted about these samples was that haze and partly cloudy were two labels that we found hard to distinguish between, and because essentially they kind of had very similar properties. So that is something that we had to tackle. We tried to tackle while we were on our project. If we move to the next slide. So based on the issues that we had and the performance that we had up till that point, we tried to make two modifications in order to hopefully improve on the performance and the kind of labeling that we saw. So the first thing that we tried to implement was integrating a guided image filtering technique in order to remove haze, which was basically, we used the CV2 library in Python in order to remove dark shadows and such. I would not be going into the details of that right now. We can talk about it later or like at the end during the Q&A session. And the second kind was combining man-made activity labels, which was basically in order to reduce the amount of class imbalance that was present or the number of rare classes that were present. We just combined all the man-made activities like agriculture, roads, cultivation, habitation, etc. into a single label, called it as man-made, so that we can just broadly classify human interference and still be able to detect human interference as the first step towards our objective. So if we move on to the next slide, this is essentially what I just talked about. Can we move on to the next slide? Yes, so this is the modification where we combine the human interference activities, and just like we had hoped, we could see that there was a better F2 score and a validation accuracy. That validation accuracy, in my opinion, or in the general opinion, is not something that we should rely on entirely, because it's the class imbalance in this particular data set is pretty high. So rather we should rely on F1 and F2, just like how Somya was explaining earlier. So here you can see that there is a good improvement in the F2 score. And if you look at the images as well as, the comparison between the initial baseline and the predicted baseline, predicted model, we can see that there was like a good distinct improvement in between the labels. If we move on to the next slide, that's it. So that's about the project that we had, and we are open to questions.
Great. We have several questions for you in the chat here. You can see here, the first question was if there was any such studies being done more for forest fires, if you know about that.
I do know there are some studies that are going on for forest fires in the wildfires in California, but I don't know the details about it.
Yeah,
So there are.
if I remember correctly, I think when we were looking at doing this project regarding deforestation, we did see a few about forest fires, which dealt with like temperature maps and heat maps. But then, yeah, I mean, I think there is a lot of work that is being done in that sector as well. Though we can't really. I don't think I can pinpoint on something for you as of this moment.
Okay.
Yeah, I think the forest fire studies are kind of complicated in the sense that there are several aspects that you can look at, like not only the geolocation of the fires, but maybe how long does it last and the perimeter that it covers. So those are some things that were covered in one of the research studies that I looked at in one of the MinneWiADS workshops on climate change AI. So if you're interested in that, you can maybe look at the climate change AI workshop for MinneWiADS. I think they have it every year.
Great. And Kara was asking what satellite data was used for this and what resolutions is it at? They're curious because they used to do similar research, and the technology, I'm guessing, has changed quite a bit.
Yeah, so this was from the Planet dataset, their own satellites, and if I'm not wrong, it was like 256 by 256 pixels and a 3.7 meter GSD.
I think they got this data set from the public data set called Landsat, and Planet has its own satellites, so they were able to label, get like more information from their satellites, and they also had their own experts who label those images.
Yeah.
So then we got another question here. Rashad's got a couple. One is, did you have to try out different combinations before finalizing on the final custom CNN architecture? And if so, could you give some guidance on how we can arrive at better performing architecture?
Yes, the answer to the question is yes, about trying out different combinations, because it's generally, like you must already know, it is a hard task to like figure out what are the number of hidden layers or the number of nodes on each layer that you would rather have. And to be honest with you, in our case, at least, we were on a time crunch, so we did not really wait for like a global optimal model that worked best for us. But I think, I mean, ideally, the whole concept is to try not to complicate the whole architecture, in the sense the more complex you make it, the more it will tend to overfit. I guess we did start off with like a baseline which had, I think, more number of hidden layers at one point, but reducing the hidden layers worked out for us. I mean, I don't really think there is like any algorithm that I could give you to be able to figure out the best working model.
Just to chip in on that, I think like if you use PyTorch or TensorFlow, I think there are some more libraries like Keras Tuner and AutoML that help with hyperparameter optimization.
Yeah.
If you're just purely relying on searching for the best hyperparameter set to improve your performance. So you can look at those Keras. There's one Keras Tuner that I know and I use, so you can look at that as well.
Yeah.
Great. And a couple of related questions specifically to the images. One is, did you use RGB images or multispectral images? And then another is, did you have to adjust the resolution during training?
I think we just had RGB images in the Kaggle competition, so we just used the RGB channels. For I don't know about the resolution. I think we resized the images and we performed some data augmentation techniques to increase the number of images that we had for training. So that's about it for the training process.
All right, and then just one quick last question to wrap things up. How much time did it take to finish the project?
I would say that it's not exactly finished, but then the amount of time that we took was, I guess, around 2 to 3 months. Especially because we were working with like Kaggle, and like they had the data set on their platform, so it took us a while because they kept modifying the data set. But yeah, I mean, I wouldn't say it's exactly finished, but it was about 3 months.
Sure, great. Well, thank you guys so much for your time today and for the great presentation. We really do appreciate it. Everybody, we do have closing remarks here at the stage if you'd like to join us for those. And then we're also doing a virtual happy hour if you'd like to join us for some socializing and a beverage for the end of the day. And we appreciate it. Thank you.
Awesome.
Thank
Thank you
you.
so much.